Good afternoon. All right. So we are ready to start our today's class, correct? And we all are aware of the fact that we are studying statistical mechanics as of now. And as a disclaimer, today's topic is a bit difficult, but I hope I will be able to make you all understand it. Okay, I will try to present the entire thing in as easy manner as possible. And I hope you all will understand it in a way that if asked in the examination, you all will be able to write it nicely. Okay, fine. So, what are the objectives of this class? What do I intend to tell you all today? That remember we had left the comparison of the MB, BE and FD statistics at the last point. In the last class, we had finished at the discussion of what is the meaning of distribution function. However, we did not see how the distribution function looks like that for the various statistical divisions over here. So, in the beginning, we are going to begin our class by knowing how the distribution functions of the MB, BE and FD statistics look like. Reminding all of you, when I say MB, it is Maxwell-Boltzmann, BE stands for Bose-Einstein, and FD stands for Fermi-Dirac, right? So we are going to first see how their distribution functions look like. Now, once we have seen the formula or the equations for these distribution functions, then I would like to take you to a new world, the world of statistical mechanics, which is actually defined in terms of something called the phase space. So today we are going to learn about something very, very new, which is called the phase space. And once you all have understood what is the meaning of phase space, if our time permits, we will also find out something called the density of states. So these are the 3 points that we will like to study today or learn today. Fine. So before I go into the later topics, let us jump to our last, where we had left the last class, that is to see how the distribution functions of various statistical mechanics, namely this MBBE and FD, look like. Okay. Now, reminding all of you once again, when I said that distribution function, how did I explain that to you? I explained that distribution function was the ratio of something called the Ni by Gi. And what is this Ni and Gi? We had considered that the system consists of various energy levels E1, E2, E3, and like that, there is one energy level which I called as Ei. Corresponding to that energy Ei, the ith energy level, there are as if Ni number of occupants in that. So as if Ni particles have the energy Ei, and that particular energy level has a degeneracy of Gi folds. In this scenario, this Ni by Gi, we had discussed that this thing is called the distribution function. And naturally, this distribution function, how the number of degenerate levels are then occupied by the number of particles, varies from bosons to fermions. Okay, so in this scenario, we are going to now look into, or we are going to compare the distribution functions of the 3 set statistical mechanical parts. Fine. So are we ready? So in the very beginning, let me tell you how the distribution function of the MB statistics looks like, how it looks like for the bosons. Okay. So this Ni by Gi for bosons can be written with a formula like this: e to the power alpha plus beta Ei. Now look into this. When we were solving our macrostate and microstate problems, we were considering n is equal to 2, n is equal to 3. We were doing the entire calculation in a very, very preliminary stage. However, when we actually come down to real life situations, this number of particles, the number of degeneracy folds, these are huge. So it's not like that this Ni by Gi is going to be as simple as 1 by 2 or 5 by 7 like that. It actually comes into form with this kind of a formula. As you can see, let me explain this to you. It comes out as 1 by exponential of alpha plus beta into EI. Reminding all of you, who is this EI? This EI is the ith energy level whose distribution function we are actually defining here. And in this scenario, you will obviously be wondering, what is this alpha and what is this beta? Correct? So in this scenario, let me tell you that in case of a Boltzmann system, in case of a system which, say like a system of gases, a ideal gas system, this alpha value is a constant. Please mention this while you are writing the distribution function in your copy as well. Now in this scenario, this alpha is a constant and this beta is actually 1 by kt. 1 by kt, where k is the Boltzmann's constant. We are actually doing Maxwell-Boltzmann statistics. And from there, actually, he was the first one to bring in all these calculations. So this k is actually Boltzmann's constant. And remember, what is this T? This T is the absolute temperature of the system, which we have already discussed to be not changing during our discussion. Fine. So T is the temperature of the system. K is the Boltzmann's constant. So beta is defined as 1 by kt. And this alpha is a constant depending on one system to other. It varies from one system to the other. Systems which are consisting of Boltzmanns. So the distribution function of a MB statistics following system is seen to be like this. So 1 by e to the power alpha plus beta ei. Do not forget to mention in your copies that alpha is a constant and beta is 1 by kt. Alright. So this is how you can write down the distribution function of a MB statistics following system. Now the second system that we are going to talk about is the BE statistics, or the system which follows Bose-Einstein. This is where our formula is going to change a little bit. And what is that? In that scenario, this formula can be written as exponential alpha plus beta ei minus 1. Please note down, all of you, that this minus 1 is not in the exponential part. It is a separate term. So e to the power this factor minus 1. So the distribution function for a Bose-Einstein statistics system is given by this general formula. And obviously in this case, this alpha has a different meaning. And what is the meaning of this? The meaning of alpha for Bose-Einstein statistics is written like this, mu by kt. I hope all of you can see this. This alpha for a boson system is given by minus mu by kt. K and T we have already discussed. This mu is called the chemical potential of the system. Remember, I can tell you that the example of bosons are photons. Belonging to every photonic system, there exists something called a chemical potential. Okay, no need to go very deeper into what is the meaning of chemical potential as of now. You just remember that this alpha that actually we have written as a general form is actually minus mu by kt. K is Boltzmann's constant, T is the temperature of the system, and mu is the chemical potential of the system. Now, what you can do, instead of writing like this, you can also take another step ahead and you can write e to the power minus mu plus beta plus ei by kt. You can always write that. But why I prefer to write it like this? So that when we are comparing the three, or even when we are memorizing the three distribution functions, the forms are the same. E to the power alpha plus beta ei. For Maxwell-Boltzmann, we have seen that that was the only formula. When we have come down to Bose-Einstein statistics, there is a minus 1 added to it. Just in the back of your mind, you just remember that the alpha value is changing from one system to the other. So it becomes a little easy for us to remember as well. The same thing now when I have to write it for the FD statistics, this formula now takes a plus 1 in the second term. I hope all of you, there are some questions. I have missed a few questions. What is Yusuf saying? Could you please repeat your question, Yusuf? Because I'm not able to understand what was your question. Okay, there is no light. Okay, let me try to make the condition little better. Let me try to make the condition little better. The things are not working as expected. Let me try to. I'm sorry for the delay. So now can you understand? Now can you understand what happens if I switch on the light of this room? The part of the whiteboard does not appear to be very nice. Okay, so maybe today what we have to do, because the condition is not favoring us, I would not be writing on the top part of the blackboard. So is this better now? So sorry. So the entire continuity of the class has a little bit broken down. So let me again get back. So what we were doing, where I left was, I was explaining you the distribution function of the Fermi-Dirac systems. Okay, the distribution function of Fermi-Dirac systems takes up the formula e to the power alpha plus beta ei plus 1. Remember, reminding all of you once again that when we were doing this for the Maxwell-Boltzmann system, it was only e to the power alpha plus beta ei. When we wrote this for the BE statistics, we had a minus 1 here. And now when we are writing for the Fermi-Dirac statistics, it is a plus 1 here. So if you remember this formula in this manner, it will be easy for you all to remember this. Fine. However, let me just remind all of you once again that this alpha value changes from one system to the other. For the Maxwell-Boltzmann system, it was only a constant, which was not defined as such. When we wrote this for the Bose-Einstein or the bosons, it was minus mu by kT, mu being the chemical potential of the system. And now when we are writing this for the fermions, this very formula, this alpha can now be written as minus EF by kT. Now, see, remember, we were telling that what is EI? EI is the ith energy level. Now, what I have written new, I have written something called EF. Then you must be wondering, what is EF? EF is some F level? Is it some random level? So, please understand, please remember this fact that no, this EF that I have written is not a random energy level. This is actually called the Fermi level. This is called the Fermi level. And in short, if I had to tell you, what do I mean by Fermi level? Suppose this temperature of the system is 0 Kelvin, which means when the system has been taken to, hypothetically obviously, when the system has been taken to absolute 0, the highest energy level which is occupied is called the Fermi level. This is actually in a theoretical manner that they have defined it, because we are already discussing about the Fermi-Dirac statistics. It was done by Fermi, and hence this level was called the Fermi level. I think when you study semiconductors also, you must have come across this term Fermi level. Here, how we are defining Fermi level? We are defining Fermi level as the highest occupied level of energy when the system is at absolute 0. It's not at room temperature, remember. So we are defining Fermi level as the highest occupied energy level when the system has been taken to absolute 0. That's all. So at this moment, we have now written down all the three distribution functions. So as I had told you yesterday only that all of you please make a table and write down individually like this, because of the shortage of space, I'm not able to utilize the entire thing, and I'm not able to have all the three together so that we could see and compare. But I hope all of you are having that in your copy so that it becomes easy for you to read later on. Fine. So once that we have seen that the forms of distributions are changing from one system to the other, now I want you all to think about one situation. See how we have defined this entire distribution function with the help of the ratio of Ni by Gi, where Ni is the occupation number, as in how many particles are occupying that particular energy level, and we have also talked about this G. We have also talked about degeneracy. Now, starting from this point of degeneracy, I would like you all to come with me to a new world of statistical mechanics. I'm now going to take you to a world where we are going to call that space, that world, as the phase space. But why? Why am I taking you there? Why do I want you to understand about that? See, whenever we have done this calculation, whoever did the calculation, thankfully for us, that person must have had the idea that what is this value of Gi, which means for a corresponding energy level, how many degeneracy existence is there, how much, by what fold is this energy level degenerate, that information must have been there with that person. Only then they could calculate this entire distribution function Ni by Gi. Unless I know what is my Gi, I will not be able to do any type of calculation. So from where did they get that? From where did they have the idea that, say, one energy level is divided into how many quantum states? See, I am using a term called quantum states here. Let me just make it a little bit easier for you all to understand. If you have understood the question that we are going to answer, it will obviously be easy for you all to understand the answer as well. So first, let us try to follow what is our question. What do we want to know? Say this is my energy level E. We have seen, maybe when we were solving the Schrodinger's equation, we had seen that one energy level can have degeneracy. It can have threefold degeneracy, it can have fivefold degeneracy, which means there is a possibility that there is one shy 1, there is another shy 2, there is another shy 3. So there are different wave functions or different quantum states. However, all these three have the same energy, say E. When more than one such state has the same value of energy, we call this as degeneracy. And if any particular energy level has, say, 3 such states available, we call it as threefold degeneracy. This is exactly our G. So as if when I am thinking about one ith level, I want to know what are the number of such possibilities. Is it 3? Is it 5? Is it 500? How much? This is what we are going to learn when we actually go into our phase space. So with the help of the phase space and by taking our calculations to the phase space, today we will see how to calculate this G, how to calculate this degeneracy or the number of states available for a given energy. Alright, so now let us go into our new space of space which I was calling as phase space. Now up to this much I guess is redundant today. So I will be writing below this. Fine. So let me bring this new term for all of you, which I am calling as phase space. Now this is the new term that I would like to explain to you. Now when I say space, when we are in our real world, when I say space, what is space? Space is constituting of 3 dimensions. In Cartesian coordinates, it consists of the x-axis, y-axis and z-axis. Correct? So we are in case of a Cartesian coordinate system or our real life, what do we have? We have 3 mutually perpendicular axes, say x-axis, y-axis and z-axis. And when I say space in general, I'm talking about a space which is in this 3-dimensional world. But now, when we go to this phase space, what I am calling as phase space, this is no longer a 3-dimensional space. Please try to understand. This is an imaginary space which is not consisting of only 3 position coordinates. It is a 6-dimensional space. It is a 6-dimensional space. I know it is little difficult for us to understand or visualize that there is a 6-dimensional space. But see, how are we defining the 6 dimensions? We are defining these 6 dimensions in terms of x, y, z, which means suppose there is a point on in space. In normal space, if I was asking you what is the coordinate of this space, what will you tell me? You will write this as x, y, z. The coordinates of a given point can be written as x, y, z in a 3-dimensional regular world, regular space. But when we have to write the coordinates of phase space, a particle's coordinates in phase space, along with these x, y, and z, now we have 3 more quantities. And what are they? Px, Py, and Pz. Which means along with 3 position coordinates, we are bringing in 3 momentum coordinates. Right? So if x, y, z are our 3 mutually perpendicular axes, as if now there are imaginary 3 more. But those 3 are not telling us about the value of position, the value of x, y, and z. They are now telling us the value of the momenta along the 3 position axis. Is this clear to all of you? Right? So phase space, from now onwards, whenever you hear this term phase space, please remember that we are no longer in the 3-dimensional world. We are now talking about a 6-dimensional world where 3 of our coordinates are like normal x, y, z, and the 3 are momenta. The momentum along x-axis px, momentum along y-axis py, and momentum along z-axis, which is called pz. All right. Now, you might be wondering that what was the requirement of bringing in px, py, pz? Why are we bringing it at all? See, whatever we do in physics, everything has a very deep meaning. Suppose I know that a particle in the phase space, in this 6-dimensional space, is having a coordinate of x, y, z, px, py, pz. If I know what is its value of px, py, pz, if I am aware of this value of px, py, pz, what will I be aware of? I will be aware of its total momentum. Correct? I'll be aware of its p. And when I know its p, I can easily find out p square by twice m, which is its kinetic energy. Correct? And when I'm aware of its position coordinates x, y, z, remember, the potential energy of a system varies or is always a function of the position. So when I am actually aware of this x, y, z, I can know what is its potential energy, and when I know what is its px, py, pz, I can calculate its kinetic energy. And actually, when I know all these 6, what I actually know is the total energy at that point. So this phase space is actually, you can say, another version, another way of thinking the whole world in terms of energy. Fine. So since we are mostly interested in kinetic energy, we always bring in this px, py, pz for our calculations, and hence the phase space has been designed in a manner, has been formulated by the scientists in a manner that not only the position coordinates, it incorporates the momentum coordinates as well. So if you all have understood this part, now let us move little bit ahead. Okay. So this is a point in the phase space which can now be written as x, y, z, px, py, pz. Fine. Now remember, when I have written about this 6 points, I have assumed the fact that this system consists of only one particle. Correct? So corresponding to this one particle, I have x, y, z, px, py, pz. In case that I had a 3-particle system, then what would I have? I would have an x1, x2, x3, px1, px2, px3, like that. So I'll be dealing with 9 coordinates. So in a general 3n coordinate system, a system where there are 3n number of particles, I would be having 6n number of coordinates. This is what you have to always remember. Fine. So that's all for this time being, that you need to understand that this x, y, z, px, py, pz is basically for one system. Okay? Fine. So now in this scenario, let us try to learn something more. Now my question is, how do I write? Now the notation, I forgot to tell you the notation. Generally, phase space is written as a gamma. Okay, this is written as like this. So when you see this symbol and a space written beside it, you remember we are talking about the phase space. Fine. Now I would like to know that what can be, how can I find out some, say a small volume in this phase space. If I ask you what is the value of a small volume of space in normal 3D, what will you tell me? You will tell me that small volume dV is equal to dx into dy into dz, isn't it? But now my question is, not only in 3 dimension, what will be the small amount of volume in the phase space? Now see, in phase space, along with this dx, dy, dz, now we will have to incorporate dpx, dpy and dpz as well. And by notation, we will no longer be writing it as a dv, we will be writing this as a d gamma. So a small amount, a small volume in the phase space will be equal to dx, dy, dz into dpx, dpy, dpz. Correct? So now the contribution is coming not from 3 components but from 6 components. Fine. This brings me to a very, very interesting question. Please listen carefully, all of you. If I ask you, if you forget about this dpx, dpy, dpz, if when we are in the 3-dimensional world, the small volume is given by dx into dy into dz. Now, if I ask you, what is the possibility? What is the smallest volume possible in 3 dimension? Can you give me an answer? What is the smallest value of a small volume? I can take the value of this dx to as small number as possible, 10 to the power. Say I can write it in terms of 1 meter. I can take it down to centimeter. I can take it down to millimeter, then micrometer, then nanometer, then picometer, then fermimeter. I can go down to 10 to the power minus 100. For x, I can go down to minus 1000 for y. I can go down for minus 2000 for z. So actually, in the 3-dimensional space which we live in, there is no defined value of the smallest cell that can be had. Correct? Because there is no lower limit. I can take this dimension to as small value as possible. But when I take the same question to the phase space, that what will be the volume of the smallest cell in phase space, is it indefinite as well? Which means, did you follow my question? Since I can take this dx, dy, dz to as much small values as possible, can I also take this dpx, dpy and dpz also to be very, very small? And can I say that a small volume in phase space is also indefinitely small? The answer is no. There is a very, very well defined limit. And why am I saying so? Why am I saying that this d tau cannot be as small as I want? Now see, I hope all of you will agree with me that when I write it in a little different manner, can I not write this same equation as dx into dpx, dy into dpy and dz into dpz? All I have done is I have just written the terms in a little bit different fashion. Now, please look carefully into this new equation now, this new right hand side now. I am having a product of dx into dpx, dy into dpy, dz into dpz. Are these couples, are these pairs little familiar to us? X and px, y and py, z and pz. Are they coming to us in a different form that we have seen the same couple somewhere else? Please remember that dx, dpx, dy, dpy, dz, dpz are the couples, are the pairs which we have seen in Heisenberg's uncertainty principle. right? Do we remember that this dx dpx, dy dpy and dz dpz cannot be anything. They are always greater than, if I may write it, delta x delta px is always greater than or equal to h cut by 2. Remember? So when this delta value is written to be very small, I can replace it with a small d. So dx dpx is always greater than or equal to h cut by 2, which means this factor cannot be as small as possible. It has a limit. In the same manner, this couple also has a limit and this couple also has a limit. Correct? So when I am when I am trying to calculate the smallest volume of phase space cell, it is not indefinitely small. Now see, instead of writing h cut by 2 and all, what I am writing is, say this is of the order of h. I am taking an approximation here. So I hope all of you will agree that from here, this value is comparable to h. This value is also comparable to h. And this value is also comparable to h. So however small I take the value of dx, dy or dz, in the same limit, dpx, dpy and dpz will increase so that their products will be of the order of h. Correct? So in this scenario, the smallest volume of a phase space cell can be only of the order of h cube. The order of this cell cannot go less than that. It can be greater than that as to whatever be the value. However, when I am trying to know the smallest volume in a phase space is of the order of h to the power 3, h cube. So is this clear to those who were there with me? That when I am finding out the smallest cell volume in phase space, it comes out to be h cube, right? Please let me have some feedback. That you all have followed this. So which means that if this cell is not indefinitely small, the energy value also cannot go down to any arbitrarily small value. There has to be some limit actually. Acha. Now Krishnandi is asking why we are not taking it as h cut, or see, h is 6 point something into 10 to the power minus 34. When I divide it by say 2 pi, the value will still be something into 10 to the power minus 34. It is the order which is more important here instead of the exact value. Since we are already going into decho, c into 3, h to the power 3, which means minus 34 into 3 times, so almost minus 100. Over there, it is the order which is more important instead of the exact number. Okay, so obviously we are going into an approximation. However, that approximation is good enough for us to understand the fact. Okay. So if this is so, now let me take you to a new question. Now that I know that the smallest volume of the phase space has say a volume of h to the power 3. Now this brings me to the question that how many number of such cells, how many number of such small, say there is a small volume, what will be the number of such GI? Remember we were talking about GI, the number of these cells possible for the energy level EI. Now we are going to find out the number of such cells, in the phase space which are available or which are possible within the momentum range P and P plus dt. Reminding all of you once again, this P is the linear momentum. Linear momentum is not a quantized quantity. It is a value, its value can continuously vary. So the question that I have asked is, when I know what is my smallest volume and I can also calculate the total volume, See, why am I telling you that I can calculate the total volume? Because I know that delta gamma is dx, dy, dz, dpx, dpy, dpz. So when I integrate it, if I want to know what is my total phase volume, what will I do? I will integrate over the entire thing. So I will integrate over these and I will be able to calculate the total volume in my phase space. So see, I know what is my total volume and I also know what is my smallest volume. So now the question arises, if I want to know what is the density of state, what will I do? I will calculate the total volume and then I will divide it by the volume of the smallest cell and that will give me my degeneracy. That will give me my density of states. Correct? That will give me the number of states available within that range. Correct? So this is what we are now going to do. Now let me write down the topic little bit clearly so that it becomes easy for you all to note it down. So what are we finding out? We are finding out the number of states available between momentum P and P plus dP. See, I am in a phase space. I am in a world of 6 dimensions x, y, z, dpx, dpy, dpz. When I add up all the contributions from dpx, dpy, dpz, I have the total momentum. So when I know the momentum P and I am increasing it by a value, say P and P plus dP, then within that range of momentum, how many number of such states are available? See, if you just think in this manner that I had an energy level E and I could say I could have a threefold degeneracy there. There was one space, there was another space, there was another space. So 1, 2, 3. So for a given energy value E, I had threefold degeneracy. Now that was a very, very small example. Now when our world has increased, when we have come down to the phase space, now I am asking is how many such cells is possible? How many such quantum states are possible within the momentum range P and P plus dP? Okay, this is what we are now going to calculate. Is this clear to all of us? And we call this number of states available between momentum P and P plus dP as density of states as well. Density of states as well. They are the same. Remember in the very first slide, when I was starting and I was telling you what I am going to teach today, I had written the term density of states. That density of states is actually the same as this. Fine. So now let us go ahead and try to calculate this. I know this mathematics is very, very abstract. You're not able to visualize it. You're not able to actually digest it so easily as I am telling you. But just take some time to sink this in. Let us do the mathematics first. Then let us discuss once again so that the things become a little easy for us. Okay. Now, this number of states, please remember, this number of states within the momentum range P and P plus dP has a name. We denote it as G, Gp, dP. So see, instead of the ith level degeneracy, which was completely defined, G, number of states in the ith level, now as if I have broadened my picture. Instead of just telling ith level, I am actually trying to find out what is the number of states possible within the momentum range P and P plus dP, and that, as I told you, is written as Gp dP. Alright, G, a function of momentum, and within the small range of dP. Okay. So this Gp dP will be how much? Will be the total number of states, will be total volume of space within this momentum range. And within this momentum range, what is the total volume? It is Let me just write down first, then it will be easy for you to understand. Dx, dy, dz. I have put three integrals because see, this is a volume integral. I will have to integrate dx separately, dy separately, dz separately. So we are actually having three integrals. So it is three integrals of x, y, z and three more integrals of dpx, dpy and dpz. And where is this dpx, dpy, dpz? Within this dp, within this value of dp that we have defined from p and p plus dp. Within that, this momentum range is available for all of us. So if this is the total volume, when I divide it by the smallest volume h cube, I will have the number, right? Are you following me? I will have the number. Say, I will give you an example how to understand it. I always give the same example time and again. That is, say there is your classroom, the first row. First row, it is having a volume. Now, first I will see that this first row, there are 3 seats. But I say I did not know how many seats are there. I know that there is the row. This row consists, say, a volume V. And I know that the smallest chair has a volume, say, V1. Then how will I calculate the total number of seats? I will take the total volume divided by the smallest volume, which is, say, V1. So V by V1 will give me the number of seats available. In the same manner, when I am finding out the states in our phase space, within the momentum range P and P plus dP, what will I do? I will write down the total volume within that space and I will divide it by the smallest volume possible. And that will give me the number. Correct? Very nice. So when you all are giving me this much of confidence by saying yes ma'am, I think I can move forward. So this is now to be calculated. I know this is not very easy, but at least we will try. So this is where we are standing. Now see, when I integrate over the normal space dx, dy, dz, what I am going to now write it as, because it has already been done, we write generally the volume of the normal space as a volume V. Let us assume that this, when I have integrated this dx, dy, dz, this has come out to be V. Some volume V. Okay, since integration of dx, dy, dz is going to give me a big volume, I have written that volume as our known term of volume capital D. Okay, so this V into this integration of dx, dpx, dpy, dpz divided by h cube are the number of states available. That is the density of state. Now the question arises that how will I evaluate this part? Can you all see? Okay. So how to calculate this integration over dpx, dpy and dpz? If all of you have understood till now, let me just go into the fact that how to calculate this dpx, dpy and dpz of integrations. Fine. We are almost done. Do not worry. Now, since out of our 6 dimensions, x, y, z has already been taken care of. It has been taken care of with the help of volume V. Volume V remains constant, so we are taking it as a constant. Now, we are going to look into the space in a little different manner. And how is that? Now, I am in a world where I have 3 axes, but these are not the position axes. This is, say, px, this is my py, and this is my pz. Fine. Now, in this scenario, when I have these 3, what am I trying to do? I am talking about the range of momentum p and p plus dp. Now, reminding all of you that p is a vector in this world. Say this is that p. This is that p vector in this space. Now, when I write, say this is my p, this is the value of this p. Is it not? Are you not able to visualize or understand the fact that this is not just one vector which I have written down like this? This p could be here. This p could be here. It could take any value on actually a sphere of 3 dimension. Just like a ball whose radius is p. Correct? Because this p, when I have said this is my P, and this is my vector. This can actually take up any particular orientation, here, 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 and hence it will be actually on a 3-dimensional, a 3D sphere, correct? So my P is actually any particular vector, any particular radius of a sphere of radius P. Now consider another little larger momentum, which is P plus dP. Correct? So what about this sphere? This sphere will be having a larger radius. This sphere is having a larger radius of P and P plus dP. Correct? Now the question is, what is this volume? What is this volume? When I am forgetting about the entire thing, this was P and this was P plus dP. But this particular extra dP, this extra shell, the volume of this extra shell is actually nothing but our integration of dpx, dpy, dpz. Alright. Remember, from where did I get this dpx, dpy, dpz? It was the value within P and P plus dP. Correct? So, within P and P plus dP, I will be having contributions from dpx, dpy and dpz. And that actually is nothing but the integration this. So, when I am actually calculating the volume of integration dpx, dpy, dpz, which volume actually I am trying to find out? I am trying to find out the volume of this shell. Which shell? The shell of the sphere whose inner diameter or inner radius is P and the outer diameter is P plus dP, which is as thick as dP. Okay? So in this scenario, if I ask you how to find out the volume of a spherical shell, what will you tell me? I hope all of you will agree with me if I write that this shell is nothing, the volume of this shell is nothing but the surface area of this smaller sphere, surface area of the smaller sphere multiplied by this thickness. Correct? I am trying to find out the volume of this shell. So what will I do? I will calculate the surface area of this smaller shell, of this smaller sphere, and then multiply it with this thickness. That will give me the volume of this. And what is the surface area of a sphere? If the sphere is of radius r, my surface area is 4 pi r square. Correct? So in this scenario, when we are talking in terms of momentum, the surface area of this sphere is 4 pi p square. And what is the thickness of this? This thickness is dp. So the volume integration dpx, dpy, dpz is actually 4 pi p square into dt. Okay? Alright, so you want me to tell once again that how do I get the integration of dpx, dpy, dpz? Sure, I will tell once again. See, what are we? Where are we? We are actually trying to find out the number of states, the number of quantum states available within which range? Available within the range of momentum P and P plus dP. The small range is dP actually, between P and P plus dP. And this dP will be having a contribution from dpx, dpy, dpz. So small dp is actually dpx into dpy into dpz. Correct? So if that is so, when I want to know the entire thing, I will integrate over dpx into dpy into dpz. Right? But then, remember, this dp is not just any dp. It has been defined within P and P plus dP. So I do have my limits. It will start from a value P and it will go till a value of P plus dP. So within that scenario, I have taken this world to be a three-dimensional world with the three axes Px, Py and Pz. And then I have shown you that actually this dpx into dpy into dpz is nothing but the volume of this shell. The volume of this shell, which shell? The shell of momentum sphere between P and P plus dP. All right. So is this clear now? This particular ID, I guess, is Debargo's, if I remember correctly. So Debargo, is it right? Either Debargo or Shobhik. I will not be confusing anymore today. So is this okay? Okay, fine. So I have is okay. So then I think the rest of you are also okay with me. Sorry, Shobhik, I always tend to forget this. I mean, I hope you have understood that this is the shell. It is this shell which is in between P and P plus dP. Okay. So when I have integrated, when I actually want to know what is the volume of triple integral dpx, dpy, dpz, is nothing but 4 pi p square into dp. Fine. So now taking all these result into our initial equation, our initial equation can be written now as gp dp. Remember we already had this v by h cube, where v was integration of dx dy dz, and now we have 4 pi p square into dp. Now you might be wondering that why did we do it in this manner for p? Why didn't we do it for x, y, z as well? Why didn't we write it as 4 pi r square dr? Remember, we are now considering everything in terms of momentum. Our left hand side is only a function of momentum. It is not a function of position at this time. Hence, when we are calculating the total volume, we are keeping the volume part in the normal space volume part as a constant v. And we are doing all the mathematics in terms of momentum. All right. So this is how the number of states or the degeneracy possible within the momentum value P and P plus D. So when I have written it like this, now I would like to add up one more information. And what is that? When I was telling you about x, y, z, dpx, dpy, dpz, in terms of our quantum numbers, if I remind you, all of you, about the Pauli's exclusion principle, and remember we had the 4 quantum numbers: principal quantum number, orbital quantum number. They are all actually till this p. But when I have written this part, I have not mentioned the 4th quantum number, which is the spin. In this entire scenario, in this entire distribution, spin was not considered by the scientists. At the moment when they were actually doing this, the spin concept had not actually come in. So they stopped it over here only. However, now that we know about spin also, which means for all the 3 first quantum numbers same, there arises the 4th quantum number spin, which can be either plus half for an electron or a minus half for an electron, like that. Say a plus 3 by 2 and a minus 3 by 2, or a plus 1 or a minus 1 for photons. This number then gets doubled. Are you following me? Okay, Krishnendu, your question is, because we are having both terms as dp and we are cancelling this out. See, you can always write it like that. But remember, when we are actually doing the mathematics, when I am doing the mathematics, this dp is having an immense meaning. Actually, this is the variable on which I am going to do the integration. If I had to calculate the total number of states now, what will I do? I will just integrate it over gp dp. This gp is my variable where I am going to do the integration. So in case I am cutting it off, if I do not write this dp dp, actually this physically has no meaning. All right, this physically has no meaning. Otherwise, it is right. You can always write that gp is equal to 4 pi p square d by h cube. But if physical significance is what you are looking for, both sides dp should be written. Let me remind you, remember when we were doing the Lamarck-Princhin plot or the black body radiation, we used to write it as E nu d nu. We used to not write only a value of energy. We used to always write it with the d nu or E lambda, d lambda. because we were doing the integration with respect to nu and lambda. The same concept is also applicable here as well. Okay. So now if we can go forward, as I was telling you, after we have found out these numbers, now the new concept of spin is coming in. So as if these are the number of states possible for a system which has spin, this number will just be doubled. Please try to understand that when, remember yesterday I told you that when we talk about bosons, Maxwell-Boltzmann, they do not have any spin. So if I'm writing the number of states for a boson, this formula is fine. This formula is good. But when I have to write this for a fermion or a boson who have spins, then this number is not just 4 pi p square. This number can be multiplied by 2. Because for an upspin state as well as a downspin state, as if the number of states is getting doubled. So in general, what we will write, this will be so for bosons or say for MB stat. But when I have to write this for BE and FB, this will be, instead of 4p, we will write it as 8 pi v p square into 8. So instead of 4, it becomes 8. So is this clear to all of you? How we have calculated the number of states? See, time and again I am using this term number of states, number of states. Number of states means the degeneracy, the available spaces where a particle can go and sit within the same value of momentum, within the same value of say energy. How many such available seats are there? How many such available states are there where the particle can go and occupy? So this is the meaning of the number of states, and in short we can also call it as the degeneracy of that particular state, right? Degeneracy of that particular level. Very nice. So you all are giving me a lot of confidence. I was very skeptical about whether you all will be able to understand this. So now that we have brought in our GPDP part, let us go to the final result. Let me just now take you to the final result and then finish today's class, which is, once now that I have defined the number of states within momentum value P and P plus dP, can I now also define something called GEDE? Instead of GPDP, can I also write GEDE? And what will I mean when I say GEDE? GEDE are the number of available states within an energy range E and E plus DE. Reminding all of you why I am trying to bring in GEDE. Because remember, our distribution function was Ni by Gi and it corresponded to an energy value EI. So for a fixed energy range EI, I could define Ni by Gi. But now if I want to know within a range how many numbers are there, then what will I be writing? I will be writing something like NEDE by GEDE, and which will be corresponding to what? It will be corresponding to an energy of E and E plus DE. So finally we will be able to actually pull this entire calculation or do this entire phase space concept to our distribution function. Then we will be able to actually apply our distribution function and know how the entire system actually works. So if we can actually finally convert this GPDP into GEDE, our life is sorted. Our calculation is sorted. Fine. So that is the last thing we will do today, and we will finish our class. Now over here, this was the last result that we had we had agreed upon. Now over here, before I do the final calculation, I would just like to tell a very, very important sentence. And what is that? It is that now that we are going from the momentum range to an energy range, we are actually going to do this calculation for a free particle. Once again, I have been discussing about the free particle in various classes in various forms. Remember, when I say a free particle, this particle is not acted upon by any potential. Correct? Why we do this for only a free particle must be your question. That why not do it for a specific potential? The thing is, mostly in statistical mechanics, this approximation is taken. Say for example, I want to deal with free electron gas, a system of free electron gas. What is the meaning of free electron gas? Any metal has large number of free electrons and they move about within the solid in a random manner, and we consider that system as a free electron gas. Those free electron gas belong to fermions. They are fermions. So they will be following the distribution function of Fermi-Dirac statistics that we have already discussed today. And over there, when I want to know how they will be behaving within an energy range, what will I have to do? I will have to convert this thing into the energy part. But remember, when we deal with this free electrons, we consider that this free electron gas are free particles. We do not have any imposed potential on them. They act like free particles. Or we can also use the same concept for Brownian motion. In Brownian motion also, particles are randomly moving. They are also not acted upon by any external force. So, in the preliminary stages, when we do the initial calculations, we do this entire concept for free particle. Later on, for system to system, this GEDE value changes, and that is actually a very what to say, complicated manner, and scientists are still working on them. That putting in various systems, various potentials separately and doing the calculations. But what we are about to do now is to calculate GEDE considering the fact that this energy is coming only from kinetic energy. It has no contribution from potential energy. I know you all will be having a lot of questions on this. I will not be taking up the time of the class a lot. I will show you the mathematics here and we will discuss this more on in our group. Okay. So how do I convert this GPDP into GEDE is my final task. So my final task is to convert this momentum to energy. Now what will I do? I know that my total energy in this case, because the particle is a free particle, is p square by twice m. So can I not write p square is equal to twice me, right? So if I know p square is equal to twice me, I would like all of you to differentiate this particular equation. Then what can I write? 2p dp is equal to 2m dE, right? Or PdP is equal to MdE. So now that I have the value of P, so I can write P as under root twice ME, and also I know that PdP is equal to MdE. So can I not put this as, take these two values and put it into the formula? So when I take these values, when I am converting the P into E, then what will I have? This GEDE will now become, see, this P square dP is nothing but P into PdP, where P is root over 2me, PdP is MdE. So I will just take these two and I will put it in the formula. And hence I will have this formula as 8 pi V by H cube. For P, I will be having a twice ME. From PdP, I will be having a 2me dE. That's all. So when I do the little bit of mathematics, I will take this 2m. I can write it as, say, 2m to the power 3 by 2. I can write this also, E also as 3 by 2 dE. So this becomes my final answer. So GEDE is 8 pi V by H cube into all this. Is this okay? Please, I will also be giving you notes on this, where you will be seeing these calculations in a very precise manner, because writing it over here and the light is also not supporting me today much. But still, I hope that all of you have understood at least a bit of what I have tried to understand, to make you all understand. Is it okay? Was it okay? So just before I finish up the class, let me summarize whatever we have learned today. The first thing that we saw was to know what are the three various distribution functions for the three different MB, BE and FD stacks. Then we had learnt about the new concept of phase space, and then we calculated the number of states or quantum states within an energy, or rather first momentum P and P plus dP, and then E and E plus D. Okay, so you all must be feeling very happy that this class is coming to an end. I know that this was little difficult. Okay then, okay. If you are having any more doubts, we will discuss as usual. So let me say goodbye to all of you for now. See you again tomorrow. Bye bye.